Hello, Sph4u. Today we're going to explore the concepts of relative motion. Now, the concept of relative motion is basically this. All motion is relative. That means there really is no such thing as a permanent, fixed point of reference. All motion is in relation to other objects, but no one can decidedly say whether one object or not is moving in an absolute way. Here's a short little demonstration and animation that I made to sort of introduce the idea. The concept of relative motion means that all motion is measured with respect to something else. In this case, we have a fixed background of the moons and stars. Now I have introduced the first astronaut, which is also at rest with respect to the moon and the background stars. Now a second astronaut appears, also at rest to the background stars, the first astronaut, and the moon. Now, the second astronaut appears to be moving to the right with respect to the first astronaut, as well as the moon and the background stars. Now it appears that our second astronaut is moving to the left at a higher speed with respect to the background. Now, both of them appear to be moving to the right at a constant speed, but they're at rest with respect to each other. If we change the camera perspective, you can see that now. Once you remove the background, they both appear to be at rest relative to each other. Now, the first astronaut appears to be moving to the left with respect to the second, or it could be from the perspective of the first astronaut, where it appears that the second one is moving to the right, as you can see, once the stars come back. Okay, so let's elaborate on this. So when we say that all motion is relative, it means that we have to record motion, or at least describe it, from some frame of reference, or which can be an object, or a series of objects. Generally speaking, the way the human brain works is we treat the environment itself as motionless. But that actually really doesn't entirely fly. Here, let me explain. Imagine you're sitting in your room and you're just looking about around at the various objects lying around. And generally speaking, the way your brain would work, you'd say, okay, well, everything is in my room is motionless unless I physically move it. Well, how can you tell if something is moving or not? It all depends on what is happening in terms of the background. So let's bring our astronauts back here. So the way I have my astronauts set up here is they appear to be motionless with respect to the background. Now, if I grab one of these objects, right, our first astronaut, you can see the first astronaut is moving, or at least the ghost of the astronaut is moving with respect to the background. And we assume that the background is fixed. Well, in your room, the walls, the floor, the ceiling, the furniture, generally speaking, of course, aren't moving, but that is in relationship to your local area, the ground. But the earth itself is moving. So here is a bit of an experiment or a thought experiment, just to sort of explain the idea. You're sitting on a train that is traveling at 150 kilometers an hour east. Now, when we say 150 kilometers per hour east, that is measured against the ground. So relative to the train, however, you are at rest, because if you're sitting on the train, you and the train are moving together as one. So from the perspective of the train, you appear to be at rest. However, relative to the earth, you are traveling at 150 kilometers per hour east, because the train is traveling at 150 kilometers per hour east with respect to the earth. But it becomes a little bit more complex when we move off the surface of the earth. So our frame of reference, when we do this, say from space. So let's say you take some relatively quote unquote fixed point in orbit. There's no such thing. You are moving at approximately 1,500 kilometers per hour. Now, let me explain that. If you are at the equator, it's about 1,500 kilometers per hour. What that means is the surface of the Earth near the equator is rotating around the axis of rotation, which approximately goes through the North and South Pole. And the Earth does one rotation in a single day, in a 24-hour period of time. The circumference of the Earth is approximately 40,000 kilometers, give or take, at the equator, that is, of course. You're covering that distance in a 24-hour period. In order to do that, that means tangentially speaking, any point at the equator must be moving at a speed of 1,500 kilometers per hour. So even if you're just sitting and chilling at a beach near the equator, the beach and everything around you is moving. We can't really detect that motion. We don't feel the Earth's rotation, but we know that it's happening because we can see the effect from certain astronomical phenomena. The fact that the sun appears to rise in the east, sets in the west, is an illusion of relative motion, which for centuries was a huge debate. Back at around Copernicus's time and Galileo, it was still accepted belief that the Earth was the center of the universe and the sun was rotating around the Earth. Copernicus showed that, in fact, it was the Earth revolving around the sun, and Galileo further supported that argument, but it was quite contentious at the time. So it's easy to be confused about how motion actually works. Another consequence to the idea that the Earth is actually spinning itself has to do with the motion of the ocean currents. The fact that our ocean currents travel in loops. Weather systems do the same thing. Cyclones or hurricanes, tornadoes, they rotate. That rotation is a direct result of the Earth's spinning, that 1,500 kilometer hour spinning near the equator. Now, here in London, Ontario, we're halfway approximately between the equator and the North Pole. So at this point, we're traveling closer to around 750 to 800 kilometers per hour tangentially, but still just whipping along. But wait, there's even more. The Earth itself is orbiting around the sun, and it covers a substantial distance circularly, well, approximately circularly. It's more elliptical, but that's not here nor there. But basically, we approximately make a massive circle around the sun. In order to complete that distance, the Earth is traveling at approximately 108,000 kilometers per hour, orbiting around the sun. So we have even more compounded motion. And not even that, not even limited to that, the entire solar system is hurtling through space. We're on the distant arm of the Milky Way, basically in the suburbs, and we are rotating around the center of our galaxy. And interestingly, not just in a regular pattern, but kind of like the way a merry-go-round goes, where the solar system is actually oscillating up and down as well as rotating. And then on top of that, the entire Milky Way itself is moving. The main point is that all motion is relative. If you go further back, you'll see that there is no fixed point in space that you can make a reference to. We just make a local reference when we're describing motion. And that is a very, very important concept to understand. So because of this complexity of relative motion, we have notation that helps us keep things straight. So you're familiar with velocity as a vector, but here we have a couple of subscripts. One is a prescript and one is a postscript, pre-subscript, I guess, and a post-subscript. And this is how this reads. YVT would be your velocity with respect to the train. Your velocity with respect to the train would be 0 kilometers per hour. However, your velocity with respect to the Earth, that would be 150 kilometers per hour east, but that is in relation to the Earth itself. Your velocity with respect to the orbit is 1,500 kilometers per hour east. Well, I guess I should have added the 150, but whatever. It's not nor here nor there. And then your velocity with respect to the solar system is approximately 108,000 kilometers per hour, counterclockwise, depending which perspective you're looking. So if you're looking from the top, I guess counterclockwise, which means above our North Pole, or if you're looking the other way, it would be clockwise. It all depends on your perspective. And why do we consider the North Pole up and the South Pole down? Again, that's just arbitrary. Let's take a look at this first example here. Example 1, we have a passenger on a train traveling at 150 kilometers per hour south. Now that's the train that's traveling at 150 kilometers per hour south. Our passenger walks to the back of the train. Now this is very important. Walks to the back of the train at 3 kilometers per hour. Now, logically speaking, if the train is traveling south and you are walking to the back of the train, back must be in the opposite direction of south, which makes that north. So what we're looking for is the passenger's velocity relative to the ground. So let me show you how to make the equation so that we get the math right. So we are looking for the passenger's velocity with respect to the ground. And the equation is going to be as follows. And I'm actually going to remove the highlighting here just to explain the big idea. So notice how it starts with P for passenger. Well, on the right-hand side of the equation, we also have to start with the letter P. The last term ends with a G. So passenger's velocity with respect to the ground. And our last term here ends with a G. And then when we connect the two, we have a T sandwich. So it goes PVT, TVG, and that is equivalent to PVG. So why does this work and why does it have to be in this particular format? Let's take a look at this little example off to the side here. Let's say we're trying to get from point A to point C. Well, we can go from point A to point C directly like this. Or what we can do is we can go from A to B, then from B to C, and that will get us to the exact same spot. Well, A stands for position A, C stands for position C, and then B stands for position B. Well, these are actually all technically displacements. And if we look at this as a vector equation, the displacement from position A to position C is equivalent if we add the displacement from A to B plus the displacement from B to C. Because when it comes to displacement, all that matters is the starting position and the finishing position. So you can either go directly from A to C, or you can go A to B, then B to C. So basically, this pathway here gives you the same result as this combined pathway here. They are equivalent because they get you from the same position starting to the same position ending. And if you notice the notation, we start with an A, we start with an A. We end with a C, we end with a C. And then we have our B sandwich. Now let's solve the problem. So we got TVG, which is the train's velocity with respect to the ground, and that's 150 kilometers per hour south. Then we have the passenger's velocity with respect to the train, and that is 3 kilometers per hour north. So here's our vector equation, and that's PVG is equal to PVT plus TVG. And the important thing is don't forget to get your sandwiches. So it starts with the P, starts with the P, ends with a G, ends with a G, and there's our T sandwich. The vector diagram always starts with our first vector here, which is our PVT. So we start with PVT, then we add TVG, which is our second vector here, and PVG is our resultant. As you can expect, it will go south. Now solving it algebraically, since these vectors are collinear, we can drop the vector notation and then just replace PVT with positive 3, because that is going north, plus negative 150, negative because it is going south, and the passenger's velocity with respect to the ground, or at least the magnitude of that, is negative 147. And my only regret is, from a notation point of view, I made a small mistake in my note. Those should be scratched out because we're not in actually vector mode anymore. We're using scalars. But in the concluding statement, that negative is interpreted as south. Now, a small little side point in terms of the way these relative motion vectors work. TVG stands for the train's velocity with respect to the ground. That's 150 kilometers per hour south. But sometimes when you're solving these, to make the vector sandwich work more easily, you have to flip the vectors. So from a relative point of view, the train is moving at 150 kilometers per hour south, but with respect to the ground. But if you're on the train, it appears actually that the ground is moving north. Most people recognize that it's them that's traveling on the train that's moving. But if you stare out the window of your train that you happen to be a passenger on, and you look at the ground, you can imagine that it looks like the ground is going in the opposite direction of the motion of the train. So in this case, the ground's velocity with respect to the train is 150 kilometers per hour, but north. So therefore, what we can conclude is that the ground's velocity with respect to the train is the negative of the train's velocity with respect to the ground. And we can prove it mathematically by manipulating the equation a bit. So we can rewrite our equation like this. The passenger's velocity with respect to the ground plus the ground's velocity with respect to the train is equal to the passenger's velocity with respect to the train. Now, we already know this answer to be 3 and north. So when we substitute our values in, PVG was 147 kilometers per hour south, so we got a negative 147. And the ground velocity with respect to the train is 150 kilometers per hour, but north. Well, when we combine these, we get a value of positive 3. Therefore, our PVT is positive 3 kilometers per hour. And I believe it should have been 4 sig figs. Relative motion is an absolutely essential concept to work with when you're dealing with navigation, specifically aeronautical, so air and sea essentially, because factors such as ocean currents and winds affect the motion of boats and planes. Planes obviously being affected more so by the wind, not the oceans, but if you're in a boat, you're being affected both by the motion of the ocean as well as the intensity of the wind. This makes setting directions challenging when you have to take in consideration the currents in the oceans or the currents in the air. So in order to reach a desired location, you have to actually adjust the direction in which you are pointing your plane or your boat to compensate for those other factors such as wind or ocean currents. This is where the terms heading and bearing come into play. The concept of heading. This refers to the orientation of the object that is experiencing relative motion. Basically, it's the direction that the actual object itself is pointing. So when we're talking about the heading of the plane, of a plane or heading of a boat, literally the compass direction that the nose of the plane or boat is pointing to. So let's say you're in a canoe in a river and you start paddling, you point your canoe due north and you start to paddle, your heading is due north. Whether or not you actually move due north is entirely dependent on what's happening with the currents. And this is where bearing comes in. Bearing is the actual direction that you travel with respect to the ground. So this is the object's resultant motion. So let's do a little analogy here. Here we have a commercial jet, and the commercial jet appears to be having a heading of due north because the nose of the plane is pointing straight up. So this vector here, this would be the plane's velocity with respect to the wind. If there's no wind, the plane will actually move north, directly north, with respect to the ground. But what if there's a wind? And what if there's a wind coming from the east? So the wind is pushing on the plane to the west. So let's say the wind's velocity with respect to the ground is so many kilometers per hour to the west. Not as fast as the speed of the plane, but significant. The motion of the plane would follow this path here that I've highlighted in red as the resultant. And this resultant would be the plane's velocity with respect to the ground. And the vector equation would be as follows. PVG is equal to PVW plus WVG. And notice, start with a P, start with a P, end with a G, end with a G. And this is our W sandwich. In this case, the PVW is north. And let's say the wind throws the plane off by 30 degrees. So this heading would be north, but the bearing of the plane would be the direction of the resultant, which in this case would be north, 30 degrees west. And that would be the bearing. Let's take a look at our first sample problem, the river crossing questions. In the very first example that we did, all the vectors were collinear. So we're going to take a look at how to solve these problems when the vectors are not collinear. So in this example, which actually is our example 2, but our first example with non-collinear vectors, a boy can swim at a maximum speed of 2 meters per second. He dives into a river with a current of 1 meter per second south. Part A asks what the boy's velocity with respect to the shore is if he maintains a heading of due east. So let's focus on this first. WRT stands for with respect to. So since we're referring to the motion of the shore, the notation is BVS, boy's velocity with respect to the shore. Now, what we were given is the magnitude of the boy's swimming speed of 2 meters per second. So this represents the magnitude of the boy's velocity, but with respect to the river, not the shore. So that 2 meters per second, in this case, will be east. because the heading is associated with the buoy's orientation within the water itself. Now, with part B, it asks what would be the buoy's heading this time. So in part A, we know what the heading is, but what we don't know is what the bearing is going to be. So again, the heading is the direction in which the buoy is oriented within the water. So he is pointing east, but the river is moving towards the south. So the resultant motion with respect to the shore is going to have an east and a south component to it. So as you can imagine, the bearing is going to go east so many degrees south. But in part B, we're asked for something a bit different. In this case, we're trying to figure out what heading the buoy should have in order to maintain a bearing of due east. Now, the bearing always refers to the direction of the resultant velocity. So in part B, we know the direction of the resultant, but in part A, we know the direction of the buoy's velocity with respect to the river. So that's the difference between the heading and the bearing. And then part C, it's a follow-up on part B. We're asked to find the buoy's velocity with respect to the shore. So part B, we're looking for an angle. In part C, we're looking for the magnitude of the resultant as well as that angle that we found in part B. So in this particular question, B stands for the buoy, of course, R represents the river, and S represents the shore. So for part A, as you can see the way I have written the information, BVR, buoy's velocity with respect to the river, is 2 meters per second towards the east. The other vector we know is the river's velocity with respect to the shore, and that is 1 meter per second south. Now in part B, the given information has to change a little bit. The buoy's velocity with respect to the river, we know the magnitude of that. The buoy still can swim at a maximum speed of 2 meters per second. But in part B, we don't know what the direction is. We still have the same velocity with respect to the river and the shore. So the river still has a velocity with respect to the shore of 1 meter per second south. It is still traveling at the same rate. Now, we lost a little bit of information, and the information that we lost was the direction of the heading, but what we gained was the direction of the bearing. So the resultant velocity is the buoy's velocity with respect to the shore. That magnitude is unknown, and that is what we're trying to find in part C, but we do know the direction of it. We will obviously address how to solve part B when it comes time to it. But in the meantime, let's just focus on part A. And I just realized there was a technical problem when I made the note on Microsoft Word. For some reason, this is supposed to be. Let's scratch that out. And that's supposed to be part A, B, and C. Didn't notice it. Oh well. So for part A, we're looking for the buoy's velocity with respect to the shore. And part B, we're looking for the heading. And part C, we're looking for the buoy's velocity with respect to the river. Except we're not doing that. My bad. Oh, I'm going to have to re-edit this note. Buoy's velocity with respect to the shore is what that's supposed to say. Okay, so let's start off with part A. And we're going to start off with our vector equation. So the buoy's velocity with respect to the shore is equal to the buoy's velocity with respect to the river plus the river's velocity with respect to the shore. And again, to make sure that we have the right formatting, we start with a B. We start with a B on the right-hand side of the equation. We end with an S, and the last vector must end with an S. And of course, we must have the R sandwich in between. Now, the thing is about this notation, it is very effective in terms of building the vector equation, but then becomes quite cumbersome when working with the actual practical vector analysis. So what I like to do is I prefer to give what I refer to as short names. So for example, BVS is the same as the resultant. And I like to give the first vector in our list, the BVR, the name vector A. And RVS, that would be our vector B. So instead of BVS is equal to BVR plus RVS, I prefer to write it as R is equal to A plus B. It's just a little cleaner to work with. So the vector equation with this relative motion notation is great insofar as generating the appropriate formula, but then becomes less practical when you're actually doing the mathematics. So as stated, R is equal to BVS, A is equal to BVR, B is equal to RVS. Now, when it comes time to drawing the vector diagram, you start with your vector A followed by your vector B. So our vector A, that was our 2 meters per second east, and our vector B, that's 1.0 meters per second and south. Now, this theta R here, that represents the direction of the bearing because that's associated with the resultant. So theta R is the bearing, whereas theta A, that is equal to the heading, which we know is east in this particular case. So based on the vector diagram, we then make the determination on how to figure out the magnitude of the resultant. Well, the magnitude of the resultant can be found by using Pythagorean theorem. And that's because vector A and vector B are perpendicular to each other. And vector R represents the resultant. So R is equal to the square root of A squared plus B squared, which gives us R equals root 5. Now, I prefer, if we can, to have this additional line here where we have R expressed as its root value. And the reason being is if we need to use the value R for a future calculation, it is better to use root 5 than it is to use the rounded 2.24 meters per second. Now, this would be the magnitude of the resultant in 3 sig figs. However, the root 5 is a better representation because it does not involve any rounding at this point. So that's something to bear in mind. And of course, finding the angle is also a relatively trivial affair. Since it is a right angle triangle and it is best practices to use the original vectors, so we'll be using vectors A and B. So finding theta R is the opposite, which is side B, over side A. Notice I don't have my harpoons because we're just working with the magnitudes of the vectors, not the directions. So theta R is equal to the tan inverse or arctan, as I'm apt to use, which is B over A. And then we get R is equal to 26.6 degrees rounded to 3 significant figures. So then we are left with the buoy's velocity with respect to the shore is 2.24 meters per second east, 26.6 degrees south. Now, just a note, again, technically, we could have used sine or cosine to figure out theta R because we do, in fact, have the value for the resultant. If you were to use this value for the resultant, root 5, because there was no rounding, you would get this identical 26.6 degrees. If you were to use the 2.24, you would get something slightly different. So the square root of 5 is a better representation of R, but still, you should use tan and you should not use sine or cosine, even though we have an unrounded version of R. And the main reason why is that you are still subject to making mechanical error at this point. So this root 5, you could have miscalculated this. So you may have gotten, say, root 6 because you just didn't have your wits about you or something to that effect. So again, you still should avoid using this if you can. But if you do have to use a value for R, this is the better version to use, not that. Now, the next issue is how we deal with part B and by extension part C. So what's cool about this is that our vector equation is actually the same in both cases. BVS, the buoy's velocity with respect to the shore, is still equal to the buoy's velocity with respect to the river plus the river's velocity with respect to the shore. The issue, however, is in terms of the values for each vector. And the biggest issue is this. BVR, the buoy's velocity with respect to the river. Let's go back up to the givens here. We know the magnitude. What we don't know is the direction. So normally when you draw your vector diagram, so again, this would be R is equal to A plus B. We don't know the direction of vector A, so we can't start with vector A simply because we don't have enough information. So we have to do a somewhat indirect approach to actually sketching what this is going to look like. So here are the rules of how that is done. When you run into that situation where you can't draw it directly, rule number 1 is you always, first draw the vectors for which both the magnitude and direction are known. In this case, we know everything about the river's velocity with respect to the shore. We know that it is still traveling at 1 meter per second south. So we start with that vector first. Second is you draw the vector for which the direction is known. So in part B and C, we know the direction of the resultant. So we then start with the resultant. And then the last step is you draw the last vector, the one for which we don't have the direction. So let's do a little recap and giving short names for everything. So the buoy's velocity with respect to the river, which we're calling vector A, is 2 meters per second, but the direction is unknown. So we don't know that direction, so we're going to work with this vector last. Our vector B, we know everything about. The river's velocity with respect to the shore, we know its magnitude and its direction. So this is the one that we're going to start with first. And then the resultant, which is our buoy's velocity with respect to the shore, we don't know what the magnitude is, but we do know the direction of the bearing. We know that it's bearing east. So in order, it'll be this: first, second, third in terms of drawing. So we start with our vector B. So our vector B is 1 meter per second south. Next, we draw our vector R. But when you draw the vector R, this is the important thing. You need to remember that in the order of drawing, vector A is tail to tail with the resultant, but vector B is head to head. Let me show you what I mean by that. Let's go back up. So let's take a look at this vector diagram. Let's clean this up a little bit. This vector equation is the resultant is equal to vector A plus vector B. So if we look down here at the very end, the head of the resultant attaches to the head of our last vector, which is vector B. So vector B goes head to head with the resultant, but vector A attaches to the tail of the resultant. So vector A is tail to tail, where vector B is head to head. So head to head and tail to tail. That is always, always, always true. So no matter what, the first vector in your equation will always be tail to tail with the resultant. And the last vector, notice I didn't say the second one. In this case, it is the second, but the last vector always goes head to head with the resultant. So going back to here, and we'll zoom out so we can see these numbers. So again, we started off with our vector B. Then we attached our vector R. Now, we know that it has to go head to head, and vector R is going east, which means there's only one way to draw that. So vector R, the resultant, is going east. Vector B is going south. They attach head to head. There's only one way to draw this, and that is in this format right here. And then finally, to draw, and let's put our little label here, step number 2. And then finally, to draw our last vector, we know that vector A has to go tail to tail. So there's only one place to go. So tail to tail with the resultant, and then it has to attach to B because it goes A plus B. So our vector A is going to look like that, as you can see on the diagram on the right here. And now we just double check. So we've got A plus B gives us our resultant. So we know that our resultant is due east, and our vector A is going to be east so many degrees north, and this theta A represents our heading. So again, the vector equation is the same, but the vector geometry has now changed. Therefore, the way we solve this thing is going to have to change as well. So again, we are looking for the heading, or theta A. And in terms of what we know, we currently know the magnitude of A, and we know the magnitude and direction of B, but we're only concerned with the magnitudes at this point. So we know the value for B is 1 and the value for A is 2. However, in this case, B represents the opposite side, and A, in this case, is the hypotenuse. Notice the resultant is not the hypotenuse. The 90-degree angle is here now. So A is the hypotenuse, not the resultant. That is a very important distinction. You must carefully look at the diagram in order to correctly determine what relationship and what equation or technique you must use to solve for the various unknowns. So in this case, we have opposite hypotenuse. We need an angle. So opposite, hypotenuse, and angle, that straight up implies that we're using sine. So sine of theta A is the opposite, which is B, over the hypotenuse, which is A. This gives us an angle of 30 degrees, exactly 30 degrees, but 30.0 degrees rounded to 3 sig figs. So therefore, the boy's heading is east 30 degrees north, which makes sense because if the river is trying to push you south, you need to have some angle towards the north to fight the river's flow. So the y component of vector A, compensates for vector B. And if you look carefully at this diagram, vector A, and let me demonstrate, and I'll do that using blue, vector A has two components. The x component, which happens to be equal to the resultant, and then the y component of A happens to be equal but opposite to vector B. So this would be your, let's clean that up a little bit. This would be your AX, and that would be your AY. So AY is equal and opposite to vector B, which makes sense because you're trying to cancel out the effect of the river. And the X component of vector A is actually equivalent to what the resultant is going to be. Last step here, we now need to find the magnitude of the boy's velocity with respect to the shore, or we're trying to find the magnitude of the resultant. The most common mistake is students still think that the resultant is the hypotenuse, but it is not. So do not get the following two equations confused. The vector equation is R is equal to A plus B, but that is not related to what the Pythagorean theorem equation gives us. R equals A plus B just simply means that the resultant is equal to our vector A plus our vector B. But finding the magnitude of the resultant has nothing to do with this anymore. This part just gets us to draw the diagram correctly. After that, you have to then look at the type of triangle you have, and then you make the determination of what mathematical concept we're going to use to solve it. In this case, we can still use Pythagorean theorem. The reason why we can use Pythagorean theorem is because this is still a right angle triangle, but A is the hypotenuse, and R in this case is just one of the sides, specifically the adjacent side. That being said, A squared is equal to R squared plus B squared. And of course, we need to isolate for R squared. So when we bring B squared to the other side, it becomes subtraction. Turning the equation around, we get R squared is equal to A squared minus B squared. The opposite of R squared, the opposite of squared is square root. So we take the square root of both sides. So we get R is equal to the square root of A squared minus B squared. And the magnitude of R is 173 meters per second. So we know the magnitude of the resultant, but we also already know the direction because that was given. The bearing is east, which is associated with our resultant velocity. So therefore, the boy's velocity with respect to the shore is 1.73 meters per second east. And that does make sense when you look at the numbers. Take a look at the right angle triangle. The hypotenuse has to be the largest. B is 1 and R is 1.73. R needs to be larger than B because our heading was less than 45 degrees, but R can't be larger than 2, so it fits. Moving on to example number 3. In example number 3, we're still working with the river crossing type question here, but this time what we're trying to figure out is the amount of time, or how long it would take the boy in example 2 to cross the river if the river is 200 meters wide, and if he maintains a heading of due east. So this is really the part A of the last question. So what I've done here is I've kind of sketched the river banks, obviously a little bit uneven, and vector A, this represents the boy's velocity with respect to the river. Our vector B, that is the river's velocity with respect to the shore, and then our resultant is the boy's velocity with respect to the shore. Here is another way to think about it. So another way to look at this is the resultant is just the velocity, the resultant velocity of the boy. But this velocity has two components. It has its x component, which is represented by our vector A, the boy's velocity with respect to the river. And then it also has our y component. And our y component of the velocity is related to the river's velocity with respect to the shore. So the x component is the boy's velocity with respect to the river, plus the river's velocity with respect to the shore. So that Vx and that Vy combine to get us our velocity. Now, if we think of it in terms of Vx, Vy, and just vector V, the next part makes a little bit more sense because we're asked to figure out how long it takes to cross the river. Well, the river is 200 meters wide. The question is, along which axis is this? So this 200 meter width is happening along the east-west line. So the boy is starting from the western part of the shore and swimming towards the east. So really, the displacement along the x is equal to 200 meters east. This x corresponds with this x here because it is vector A, the boy's velocity with respect to the river, that is along the x-axis, which is what our displacement is under. And that can be highlighted here. Our Vx, let's get that up there again. Our Vx, which is our A, is 2 meters per second east. Our displacement in the x is that 200 meters east as well. And they have to be on the same axis for us to work with. You can't use the value for V and use the value for dx. They have to be aligned. So since our displacement is on the x-axis, we have to use the velocity, or the component of velocity, I should say, along the x-axis. To solve this problem is just a constant motion problem. Dx is equal to Vx times t. Now we can just temporarily drop the vector notation, so we get dx over Vx equals t, or t is equal to dx over Vx. So our displacement along the x-axis, that was our 200 meters towards the east. Our x component of the velocity was 2 meters per second, and that gives us a value of 100 seconds to 3 sig figs. How is that different now in part B? Because in part B, that's when he maintained a bearing of due east. In part B, the geometry changed. So now when we look at the diagram, we have to look at which vector of these three vectors is along the x-axis. The displacement is still along the x. And now our x component of the velocity is actually the resultant, not vector A. So technically speaking, Vx is the x component of our vector A this time. So really, it's about looking at the diagram. Whichever vector is on the same axis as our displacement, that is the one that we choose. So in this case, our Vx is our resultant value, which is 1.73 meters per second and towards the east. So doing the algebra this time, same thing. Dx is equal to Vx times t. So t is equal to dx over Vx, skipping a few steps there. And I suppose I should have put the vector notation there. And there we go. Keep with the vectors. Now our value for, these are collinear. So our value for dx, well, that gives us our 200, technically positive, over positive 1.73. And that gives us 115.6 seconds. Therefore, the time in this case is about 116 seconds rounded to 3 sig figs. So here are the interesting implications. The quickest way to cross the river in terms of time is in scenario A. So if you want to get across the river the fastest, you simply orient the body to point to the opposite shore and you swim. The consequence, of course, is you're going to drift downstream, which means that you may have to backtrack up. However, in this scenario, it takes the least amount of time. Scenario B takes more time because you're actually fighting the current a bit, which means you lose a little bit of speed, as you can see, but it has the benefit of arriving exactly across from your position that you started. So which scenario is best depends on the context of the situation. So if you're trying to cross a river that is filled with, say, I don't know, piranha, and you want to get across the river the quickest, I would do the version in section A. Just point your body across the shore and just push as hard as you can. You get over the quickest. However, if, let's say, over here, we have some dangerous rapids, and there are, of course, lots of rocks and whatnot, well, you want to make sure, in that case, that you don't want to drift down. So The second scenario, this one here, is the better one to choose. And let me actually grab my rapids and then bring them down for part B. So if you want to avoid hitting the rapids down here, so you don't mind it taking a little bit longer to get across the river as long as you don't end up in this section, then scenario B is the better one to choose. If all you care about is being in the water for the least amount of time, section A is the better choice. Yep, you're going to be thrown downstream some distance, but you're at least across the river in the least amount of time.